One way to identify an unknown substance would be to burn it. If it's a hydrocarbon, it'll make carbon dioxide and water, the amounts of which, if you're able to determine them, can be used to figure out the molecular formula of what you started off with in the first place. It sounds like it's complicated, but it's not so bad. The key thing to realize is that every time you burn a hydrocarbon, for each molecule of carbon dioxide it forms, that came from one molecule, or mole if you're doing it on that scale, of carbon. And when you form water, it came from two hydrogens in your original sample, since water contains two hydrogens. So here's a problem. You got 2.4 grams of something known as toluene, and you find that when you burn it, you get that much carbon dioxide, that much water. They're asking for the empirical, or simplest formula. Let's take that 8.023 grams and see how many moles of carbon it came from. We do need moles, right? Something like C6H8 is the molar ratio of carbon to hydrogen, so that's what we're after. There's our 8.23 grams of carbon. I think we're going to find out that that's about a fifth or a sixth of a mole, since 44 grams is a mole. And every time you form a mole of carbon dioxide, it came from a mole of carbon due to the 1-to-1 ratio there. So we could go ahead and write C 0.1823. Water looks like a similar amount. Well, it looks like about a tenth of a mole of water, but you have to remember that there are two hydrogens per mole of water. So 18 grams is a mole. It's about a tenth, but every time we form a mole of water, it came from 2 moles of hydrogen in the original sample because there are 2 H's per H2O. And so that means we have 0.2083 moles of hydrogen. This is not a 1-to-1 ratio. We have a lot of precision in our data, so we should be able to see what the actual whole number ratio is. This does account for all 2.4 grams, and there'll be other problems that don't, and we'll show that in the next example. Therefore, here's our formula. It's just not whole numbers. The way to turn it into whole numbers is to divide by the smaller number, which in this case is 0.183, for both sides. That keeps the ratio but makes one of them 1 and the other one more than 1. At that point, you can scale, multiply. Like if it was 1.5, you double everything. This happens to give you, when you do that, C1H1.143. That's very rare, and that's why we use this incredible level of precision here, because it's not till you multiply 0.143 by 7 that you get a whole number. This is C7H8. Toluene's used in paint. That's C7H8. A problem where you can have not just a hydrocarbon but something else requires a certain amount of data. Here we're identifying a substance. It's an ester called isopentyl acetate. It smells like bananas, and they tell you it also contains oxygen. Thanks for that. That helps. When we burn 1.75 grams of it, we get about the same amount of water and some carbon dioxide. Let's figure out the mole ratio of carbon and hydrogen, just like the last one. Find out how much oxygen, I should say, was present in the original sample, and do a last calculation for oxygen, giving us C, H, and O. Starting with 4.142 grams of carbon dioxide, it's about a little less than a tenth of a mole, since 44 grams is a mole, and it doesn't change when we realize that it came from the same number of moles of carbon, since they both contain 1, giving us carbon. Put it as a subscript, C 0.0941. Do the same thing for water. In this case, 18 grams of water is a mole, but each mole of water originated from 2 moles of hydrogen in your original sample, since it contains 2 in water. And we have hydrogen 0.1881, which is double the carbon, which is pretty simple. It would be nice at this point to figure out how much oxygen remains. Now in this example, there's some work that is not done to show where this 0.4311 grams came from, but I'm going to explain it to you. Realize that it doesn't show up in this slide, but here's how you would do it. You would just say CO2 is 32/44 carbon, is it not? Every 44 grams of carbon dioxide contain 12, oh, it's not. It contains 12 grams of carbon. So it's 12/44. Sorry, I did the oxygen. It's 12/44 carbon, and therefore, what's that about? A little less than a more than a quarter, less than a third, is how much carbon you had. Similarly, 2 of every 18 grams in water come from hydrogen, and therefore you would do that sort of a calculation. You add up the two, and you only get 1.3189 grams accounted for. The rest, as they've told us, has to be oxygen, which is the 0.4311 grams. Now we can take that oxygen and we can do the same sort of calculation. 16 grams is a mole. And by the way, a common error sometimes is people try to think about O2 at this point. No, we're finding C, H, and O. This is not molecular oxygen. It's a substance that contains some oxygen atoms. Let's find out how many. Well, 16 grams is a mole, and so we have 0.02694 moles of oxygen. We got all 3 of these, and we need to turn them into a whole number ratio. Divide by the littlest one, which is 0.02. Look at that. So divide by divide. That'll nicely make the oxygen 1. And let's see what it does to the other 2. I like it. A whole number for that one and a half a number for that one. Scaling is easy. All we got to do is double it up. And your final answer is C7H14O2. That is your empirical formula. If they gave you a molecular formula that was some multiple of that, then you would just multiply it out to get your actual molecular formula. So this is combustion analysis of a hydrocarbon as well as something else.